बच्चों अब मैं केमिस्ट्री के चैप्टर थर्मोडायनेमिक्स की समरी रीड करूंगी. Thermodynamics deals with energy changes in chemical or physical processes and enables us to study these changes quantitatively and to make useful predictions. For these purposes, we divide the universe into the system and the surroundings. Chemical or physical processes lead to evolution or absorption of heat Q, part of which may be converted into work W. These quantities are related through the first law of thermodynamics via delta U is equal to Q plus W. Delta U change in the internal energy depends on initial and final states only and is a state function, whereas Q and W depend on the path and are not the state functions. We follow sign conventions of Q and W by giving positive sign to these quantities when these are added to the system. We can measure the transfer of heat from one system to another, which causes the change in temperature. The magnitude of rise in temperature depends on the heat capacity C of a substance. Therefore, heat absorbed or evolved is Q is equal to C delta T. Work can be measured by W is equal to minus P x delta V in case of expansion of gases. Under reversible process, we can put P x expansion is equal to P for infinite semial changes in the volume, making W reversible is equal to minus P dV. In this condition, we can use gas equation PV is equal to nRT. At constant volume, W is equal to 0, then delta U will be equal to Q. Heat transfer at constant volume. But in study of chemical reactions, we usually have constant pressure. We define another state function, enthalpy. Enthalpy change delta H is equal to delta U plus delta N RT can be found directly from the heat changes at constant pressure. Delta H is equal to QP. There are varieties of enthalpy changes. Changes of phase such as melting, vaporization, and sublimation usually occur at constant temperature and can be characterized by enthalpy changes, which are always positive. Enthalpy of formation, combustion, and other enthalpy changes can be calculated using Hess law. Enthalpy change for chemical reactions can be given by delta H is equal to summation of enthalpies of product minus summation of enthalpies of reactants, where AI and BI are the stoichiometric coefficient, and in gaseous state by giving delta H is equal to summation of bond enthalpies of reactants minus summation of bond enthalpies of the products. First law of thermodynamics does not guide us about the direction of chemical reactions. That is, what is the driving force of a chemical reaction. For isolated systems, delta U is equal to 0. We define another state function S, entropy, for this purpose. Entropy is a measure of disorder or randomness. For a spontaneous change, total entropy change is positive. Therefore, for an isolated system, delta U is equal to 0, delta S is greater than 0, so entropy change distinguishes a spontaneous change, while energy change does not. Entropy changes can be measured by the equation delta S is equal to Q reversible upon T for a reversible process. Q reversible T upon T is independent of path. Chemical reactions are generally carried at constant pressure. So we define another state function, that is Gibbs energy. G, which is related to entropy and enthalpy changes of the system by the equation delta G is equal to delta R minus T delta S. For a spontaneous chain, delta G system is greater than 0, and at equilibrium delta G system is 0 equal to. Standard Gibbs energy change is related to equilibrium constant by delta G reaction is given by minus RT natural logarithm of K. K can be calculated from this equation. If we know delta G, which can be found from delta G is equal to delta H up minus T delta S, temperature is an important factor in the equation. Many reactions which are non-spontaneous at low temperature are made spontaneous at high temperature for systems having positive entropy of reaction.